Hi everyone, so sorry about the trouble. How are you all? Now am I audible to everyone? Now am I audible? Is the voice clear to all of you? Okay. So how are you all? How are you all? Very good evening. So firstly, send this link to your friends so that they can join this link as well, okay? They must be waiting somewhere else, but I am here now. Okay, audible? Perfect. Everyone, am I audible to everyone? Very good evening, very good evening. Oh, thank God, thank God. Oh my God. They say good things take time. So these good things are taking time. These are the good things that are taking time. So guys, today we are going to start resonance, resonating structures, stability of resonating structures, mesomeric effect, plus M, minus M, and what is the difference between resonance and mesomeric effect. We are going to cover all those topics today itself. So are you all ready? Are you all ready? Say fire in the chat box. I want fire in the chat box, okay? I want fire in the chat box. Yeah, finally. Finally, I am here. Good things take time. So today, the good thing is resonance. Resonance is taking time. It is saying, okay, I have that much importance. I will make you wait. Resonance is saying, I will make you wait for me. Right? Okay? Yes. But no matter, even if there are technical issues, we have the best technical team, right? Which is always here for your teachers, for us. They are always here. They're just one phone call away. So kudos to our technical team first. Okay? Kudos to our technical team first. So be with it. Everyone, kudos to our technical team who is always there for my students so that even if there is a technical issue, they are available for us, right? To sort all the issue. Right? Yes. Okay, perfect. So it's not just teachers, there's that team behind the teachers who are actually giving their 100%, who are working hard day and night for you guys, only for you guys. So what is your duty? Your duty is to study hard. That is your duty. Just study hard, make us proud, do practice session, ask doubts, take your test, give mock test, and then come up with the best results here. Right? Okay? Yes. So one guy is asking, Nitish is asking if ma'am, are PYQs enough? No, they are not enough. They are not enough. You need to know the concept first. You need to get into the detail of that concept. After that, firstly solve NCERT questions. For inorganic, study NCERT line by line. For organic, firstly, you need to understand the concept thoroughly, which I am doing for you. Next thing is NCERT question, NCERT exercise, NCERT in text question. Then jump to PYQs. Analyze your PYQs, and then only those PYQs will not come. PYQs combined with other concepts, questions related to those PYQs are going to come in your exam. They're like PYQs based question will be asked in the exam. Not exactly that PYQ will be asked. Okay, cool. Okay, perfect. Ma'am, my only chemistry hope is you. I am here. Don't worry. If you're leaving your chemistry on me, you're on the right track. Don't worry. Okay. So we're going to start now. Firstly, let us see the quiz for result 24th December. The result for 24th December. So first is Sneha. Kudos to Sneha, who has scored 631 out of 720. Is Sneha present here? Is Sneha present here? Next is Mahasweta, 534 out of 720. Wow. Then Rutuja Patil, 499 out of 720. Very good, very good, very good. Perfect. So happy for all of you. So happy for all of you. So if you want to be here, if you want to see your name on the screen, you need to give the test and you need to score in the top 3. Okay? Sugamanu. So, yesterday only, Gopika ma'am taught me a word that is Sugamanu. That means, are you fine? Right? Yes, I am fine. Sugamanu. So actually we are teaching each other some new languages, right? So that we can connect better. So I can connect better with my students, right? That is the, I don't want this language barrier to be there between me and my students. So that's why I'm learning few words, not that much, but I'm trying my best. Okay? Yes. Perfect. Perfect. Okay, so guys, let us start. So we're going to start. Ma'am, where is the test? Okay, so guys, in the description, you will find a link for your test. So the test is going to conduct on Friday as well as Sunday. Friday, there will be a small quiz. And on Sunday, there will be a proper mock test. There will be a proper mock test of your all three subjects. It will be like a exam only, right? So Sunday, every Sunday you will have one mock test, right? The link will be in the description as well as the link will be provided in the Telegram channel. Okay? Perfect. What Gopika ma'am is saying, why it's like so many, why there are so less likes, students smash the like button. Okay, smash the like button as the Gopika ma'am is saying. Perfect. Okay. Yes, it is. It is totally free of cost. It is totally free of cost. Okay? Perfect. So shall we start? Shall we start? Oh my God. Seriously, there's how many likes are there? I just saw the like button. You're going to give me a heart attack now. You're not going to give me heart. 50 are watching and there are only 30 likes. 29 likes. 50 students are watching here and there are only 29. You are so confused. You are so confused. Okay? Now smash the like button. Right now, I'm going to refresh my screen. Now, only 5 students have hit the like button now. Jal. I will have a look at the like button after half an hour. I'll see how many students have not done that conjugacy thing. Right? Okay. So, guys, let us talk about resonance. No worries, these. Okay, perfect. So, firstly, let us talk about resonance. What do you mean by delocalization? For resonance, firstly, you need to tell me what do you mean by delocalization. Delocalization means the electron is not in its own place. For example, if we have a for example, let's take an example. If we have a carbocation that is CH3 negative. Now this negative, these two electrons are on the carbon only, right? But if we talk about CH2, double bond CH, single bond CH2 negative. Now here resonance will happen and these electrons will jump from here to double bond and then after this pi bond will jump to this carbon and make a negative charge here. It will be CH2 negative and this will be single bond CH double bond CH2. Right? This will be the resonance here. This will be the resonance. I'm going to teach you resonance in detail. But what you can see is here the negative charge is displacing from its own place. Right? Okay. For example, one student is stick. Okay. He is standing here only. That means that person is localized. But one person is going from here, then to there, then to there, then to there. That means that particular person is not of one locality. That person has distribution of its own locality. It is sometimes it is on A place, then B place, then C place, then D place. That is called delocalization. Okay. So here the electrons are not on one place. They are distributing from here and there. That is called delocalization of electrons. And when we talk about delocalization, we have 4 things, right? We have 4 things. One is sigma bond, then pi bond, then we have lone pair, then we have free radical. So now tell me, which of these will have delocalized electrons? Which of these will have more than one? Perfect. Sharing among more than, among kya bola? Sharing among more than one. What is this? Sharing among more than one atom, right? Okay. So now, tell me, you have the sigma bond. Sigma bond means you have this carbon and this carbon, and there is one sigma bond, right? So this sigma bond, the electrons will not be delocalized here. The electrons will be present in this bond itself, okay? They are not going to displace from here and there. They are shared among this only, right? If we talk about pi bond, if we are talking about pi bonds, these pi bonds are formed by sideways overlapping, right? These pi bonds are formed by sideways overlapping of electrons. There is one electron here, there is one electron here, these are half filled, and they are going to overlap, right? This is sideways overlapping. Because of this sideways overlapping, they are going to form a weak bond, and that is why the electrons of pi bonds can delocalize. Okay, if they are in the conjugation, they will be delocalized. Okay. Now, if we talk about free radical, which we represent by this is free radical. Free radical means we have half-filled orbital. So now, this half-filled orbital is also not stable. It can also move from here to there. Okay? And if we talk about lone pair means there is one orbital and we have two electrons here. Now this is also an unshared pair of electron, and that is why it is also free to move. Now what is the conclusion? The conclusion is, out of these four, pi bond, lone pair and free radical have the ability to move from here to there, and that is why they can take part in the delocalization, but sigma bond cannot take part in the delocalization. Okay, clear to everyone? Sigma bond cannot take place. Sigma bond cannot move from here and from one place to another place, right? These bonds are static. These electrons are static. Okay, unless and until any chemical reaction is happening here, right? Okay, tell me, is this clear? Okay. So now, next is benzene. If we talk about benzene, what is the resonance happening in benzene? So, if we talk about two things, this is 1, 2, 3, 4, 5, 6, and if we have alternate double and single bond here, and we have this cyclic structure here. So, this is polyene. We have three enes, we have three alkenes here, right? This is open structure and this is cyclic structure. So out of these two structures, what we see that this structure is less stable and benzene is more stable. What is the reason behind that? The reason behind that is particular resonance in the cyclic form. Okay, resonance in the cyclic form, and that is the reason thermodynamically benzene is more stable and pi bonds are equally distributed. And because pi bonds are equally distributed here, what do we mean by this? Because as we all know, benzene, actually, we can also draw benzene by this. We can also draw benzene like this. We can also draw benzene like this. We also draw benzene like this, right? These are the two resonating structures of benzene. We can either draw it like this, either draw it like this. Either we can draw it like this. Either we can draw it like this. Now, as we know, the double bond character is shown here, so we are writing this by dot. This is also here double bond character. Here also we can find double bond character. Here also we can find double bond character. Here also we can find double bond character. So double bond character is there throughout the ring. That means we can see, we draw it like this. For our purpose, either instead of drawing this dot circle here, we are drawing simple this structure, right? This is resonance hybrid and these are the resonating structures. Okay, also named as canonical structures. These resonating structures are also named as canonical structures. Now tell me, are these resonating structures actually existing? Are these resonating structures actually existing? Or this is just hypothetical, or this is just imaginary? These are hypothetical. They do not exist, right? They do not exist. We draw it for our own convenience. We draw it for our own convenience to understand the structure easily, right? if we are making chemical reaction on this, it will not be easy for us to draw the structures. Like for example, I have to show some mechanism of reaction. I have to show some mechanism of reaction, and I'm drawing benzene like this. And I have to here. I'm going to here. There's some electrophile coming. There's some electrophile coming. The reaction is happening here. Now what to do? I have drawn the resonating hybrid here. So I'm not able to understand how will this reaction proceed. So for our convenience, what we draw is, we draw instead of this, we draw this thing. So that we are able to understand what will be the mechanism of that reaction. That is why resonating structures are drawn, but they do not exist. They are just hypothetical things. Okay? Yes. Hybrid structure is real. This is the real structure. Okay, these are hypothetical structure. This is the summation of all the possible structures, and we draw this, right? Okay, because this double bond character is existing throughout the ring, right? Okay, so now which structure is more stable? Is resonance hybrid more stable, or resonating structures are more stable? Which one is more stable? What do you understand? Which one is more stable? Resonance hybrid is more stable than resonating structures, right? Resonance hybrid is more stable than resonating structures. These are not stable. This has less energy, and this is more stable than resonating structure or any canonical structure. Okay, right? Yes. Now, someone is asking what is delocalization. Delocalization is nothing, but it is like motion of that electron. It is not static to one place. It is moving from one place to another, right? You will understand better throughout the lecture, right? Okay. So now I have shown this to you. What is the resonance in benzene? Now coming to this. Okay. Yeah, I can also draw one more thing here. If we know the carbon, carbon has 1s2, 2s2, 2p2. This is the electronic configuration of carbon. Now, if you consider outermost electronic configuration, you have 2s2 and 2p2. Now, let us see what happens here. You have 2s2 and 2p2. This is 2s, right? And this is 2p. Understood? Right? Now, every carbon in benzene, all the carbon atoms are sp2 hybridized. So, what will happen here? The hybridization will take place here, right? This hybridization will take place here. But before doing that, what will happen? This carbon, right now, this is in ground state. After this, if this is in excited state, it will be in excited state after that. Okay? So the electrons will jump from here to here. Now, this is the excited state of carbon, right? Here now, sp2 hybridization will happen. Right, this is S and this is P, this is 2S and this is 2P, right? So sp2 hybridization will take place, and there will be one pz orbital that is left, right? So now you have 3 sp2 orbitals, 3 sp2 hybrid orbitals, and you have one pz orbital, right? One pz orbital. Understand this. You have 3 sp2 orbitals and one pz orbital. Now this pz orbital, because it will form a pi bond. What is the reason? This is pz, this is another pz, this is one carbon, this is another carbon. Now they will start overlapping. They will be sideways overlapping. That is why they will form pi bond, right? There will be sideways overlapping here. They will form pi bond, and these are the 3 sp2 hybrid orbitals, where we will have 1, 2, 3 electrons. So I'll draw it like this: 1, 2, and 3. Right? So this carbon will have 3 sp2 orbitals like this. 3 sp2 orbitals like this, which will have 1, 1, 1 electrons. And that is why when we draw benzene, this is, for example, this is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and 6 carbon. So now what will happen here? This carbon is having 3 sp2 hybrid orbitals, right? So one sp2 hybrid orbital will be here, another sp2 hybrid orbital will be here, and third sp2 hybrid orbital will be here. Right? Similarly to this, one sp2 hybrid orbital, another sp2 hybrid orbital, and this is the third sp2 hybrid orbital. Right? Okay? Similarly with all these. Now, we will have one p orbital here and one p orbital here also. I'm drawing it like this. Wait a minute. I'm drawing it like this. Okay? There will be one p orbital here. Right? This is pz orbital. Now there will be electrons in all of these. One electron, one electron, one electron. There will be a sigma bond. Right? This will be one electron, one electron. This will form a sigma bond with this carbon. This will form a sigma bond with the hydrogen, atom. This will form a sigma bond with the hydrogen atom. Right? This will form pi bond with the another carbon atom. This carbon atom and this carbon atom will have pi bond. And that is why we draw the structure of benzene like this. This is carbon, this is one hydrogen, this was one hydrogen. This is the bond with carbon, this is one pi bond. Now what you will see in reality, in 3D reality, we will have in 3D reality, this carbon is also going to have one p orbital, and this carbon is also going to have one p orbital. This one will also have one p orbital. This one will also have one p orbital. So now all of these will start overlapping with each other. All of these will start overlapping with each other. Right? Understood? Have you understood, bacha? Have you understood why I have drawn the opposite sign here? Because it is positive, negative, positive, negative, positive, negative. They can only have opposite sign. Only then they will be overlapping with each other. Understood? Understood? So now this sideways overlapping will happen in all the 6 carbon atoms, and that is why we draw the structure like this. And that is why we draw the structure like this. That is why we draw the structure like this. And to represent it easily, we draw it like this. To represent it more easily, we draw it like this. Now understood why benzene is like this? Why we draw the benzene like this? The concept behind that is resonance. Because of resonance in benzene is drawn like this. Okay? And what is delocalization? This is called delocalization of electron. This thing is called delocalization of electron. Wait. Wait. Give me a minute. I am trying to use the highlighter here. I am not able to pick one. Yeah. Okay. Just give me a minute. So what will happen here? The overlapping will happen here. After that here and here and here and here and also here. So these pi electrons are not in a static position. They are traveling throughout the ring. That is called the delocalization of electrons. Okay, that is called delocalization of electrons. Clear to everyone? Okay, clear to everyone? Right? Tell me, is this clear to everyone here? Is this clear to everyone here? This was basically the delocalization of electrons. Now we are going to study the rules of resonance. Okay, rules of resonance are that in resonance only pi electrons and unshared electrons. Pi electrons means the electrons of pi bond, and unshared electrons like lone pair electrons, free radical electrons will participate in resonance. Second is actual structure is average of canonical structure. That means resonance hybrid is the average of all the canonical structure, as I told you before. Third is maximum number of valence electron rule is obeyed. That means if we say carbon is tetravalent, in all the structures carbon will be tetravalent. We have to obey the rules of octet and octet rule and valency rules. We can't say that nitrogen will form 5 bonds somewhere. If it is bonding 4 bonds, if it is forming 4 bonds, then it will have a positive charge to maintain the valency. Okay? Then position of nuclei do not change. Whenever you are drawing resonating structures, position of nuclei will never change. Canonical structure has same number of unpaired electron. Canonical structure will have same number of unpaired electron. We will see when we will draw so many structures. Energy of resonance hybrid is less than the structure. The resonance hybrid will have less energy and more stability. Right? Which is more stable? Energy is inversely proportional to stability. If the energy is less, there will be more stability. So resonance hybrid is more stable than resonating structures. After that, all atoms must be planar. So now all the atoms should be in the same plane. Right? All the atoms should be in the same plane. They should be sp2 hybridized. Okay? They should be sp2 hybridized because sp2 hybridization has trigonal planar geometry. sp2 hybridization has trigonal planar geometry, and that is why how we can say all the atoms are planar, right? All the atoms are in the same plane, right? Understood? Now, conditions for resonance. What are the conditions? Now, this is the main thing that we have started now, right? This is the main thing that we have started now. So, there are basically three conditions for resonance. First is double bond and p orbital. Double bond and p orbital. What do you mean by this? There will be double bond and then there will be single bond and then there will be one p orbital. Then there will be one p orbital. Second condition is alternate double and single bonds. That means double bond, single bond, double bond, single bond, double bond. Right? This is another condition. Third condition is back bonding. Third condition is back bonding. So, line by line, we are going to study all of this. Okay? Okay? Perfect. So, let us start with double bond and p orbital. Double bond and p orbital. So, now let us see what are the cases that it can form. So, first case can be double bond, single bond. After that, p orbital can be totally empty if the p orbital is empty. If the p orbital is empty, then it is represented by plus sign. Then it is a carbocation. If the p orbital is empty, that means it is a carbocation. So we'll write double bond, single bond and one positive sign here. Okay. If the p orbital is half filled, then what will we say? If the p orbital is half filled, we'll say double bond, single bond and free radical. Double bond, single bond and free radical. Now, if the p orbital is fully filled, there will be 2 electrons in it. Now, what to do, ma'am? Will this be lone pair? Will this be negative charge? Will this be lone pair? Will this be negative charge? Okay. Deleted. Okay. Okay. So is this clear to everyone here? There will be 2 electrons, double bond, single bond. What will happen here? Either it will be negative charge or double bond, single bond and lone pair. Now, students, tell me the difference between lone pair and negative charge. What is the difference between lone pair and negative charge? Both will have fully filled orbital, right? What is the difference between negative charge and lone pair? In the comment section, tell me. What will be the difference between a lone pair and one negative charge? Okay. So guys, if I talk about lone pair, in lone pair, both the electrons of that orbital, both the electrons in that orbital is of that atom only. Okay. If I have 20 rupees and I am spending those 20 rupees, those 20 rupees are mine only, right? That is lone pair. Now, what is negative charge? What is negative charge? What is negative charge? Negative charge means out of these 2 electrons, 1 electron is of that own atom and 1 electron it has taken from somewhere else, right? This means that there was a bond before, and this carbon has taken these 2 electrons. In this bond, the 1 electron was of carbon and 1 electron was of another carbon, right? So this carbon has taken these two electrons. Okay, so these two electrons together making up the negative charge. One is of its own and another is of, it has gained that electron from somewhere else, from the other atom. Okay. Okay. So for example, you have 20 rupees. That out of those 20 rupees, 10 rupees is yours only, and 10 rupees you have taken it from your friend. That is 20 rupees, right? 10 rupees is of your own, and 10 rupees that you have taken from your friend. So now that is negative charge. Okay. This is basically two electrons are, both these electrons are your own. This is one electron is of your own, one electron you have taken it from outside. Okay. Clear to everyone? What is lone pair and what is negative charge? Okay. Lone pairs are not involved in chemical bonding. This is the exact definition. This is the exact difference between lone pair and negative charge. Both of them can be involved in the chemical bonding through resonance. Okay. Both of them can be involved in the chemical bonding through resonance. Okay. Perfect. Now let us do. Now you understood this. These are the four cases. These are the four cases of p orbital and double bond. Double bond, single bond positive, double bond, single bond free radical, double bond, single bond negative, double bond, single bond lone pair. We are going to discuss all these cases one by one. Are you guys ready for that? We are going to discuss one by one. First is double bond, single bond and p orbital. That is double bond, single bond, lone pair. How will you make the resonating structure? So all the students present here, firstly, pick up your pen and notebook and draw these structures with me. If you are not drawing these structures with me, there is no use of this lecture. Trust me on that. If you are drawing these resonating structures along with me, only then this lecture is beneficial to you. Otherwise, this is not beneficial. This is the very hard truth, but this is not beneficial. Organic is not beneficial if you are not doing it by yourself. Okay? Perfect. Okay? Perfect? Yes. Now, how will we draw the resonating structure? If we have double bond, single bond and lone pair, what will happen here? Lone pair will be shifted to pi bond. Lone pair will be shifted to pi bond and pi bond will be shifted to negative charge. Now, ma'am, why so? What is the reason, ma'am? What is the reason for this? What is the reason? So now, see. Now, as I told you, in lone pair, both the electron is its own. Both the electrons are its own, right? So now, if you have 20 rupees of your own and somebody is taking that 20 rupees from you, you will feel sad. You will feel sad, and when you feel sad, you will be electron deficient. So now what will happen here? This X will be electron deficient because it had two electrons of its own, and now somebody has taken those two electrons from it, right? Those 20 rupees, somebody has taken those 20 rupees from you. You will feel really sad. You will be electron deficient here, right? Okay, you have to share your own electrons with somebody else, right? This is that thing. This will be electron deficient. This is carbon and this is carbon. We are not going to change the place of nuclei. Nuclei will stay in the same position. Sigma bonds will be in the same position. Only change will be unshared electrons and lone pair. Unshared electron means lone pair and pi bond, right? So now this pi bond will be shifted here. What does it mean? This pi bond will be shifted here. Now, earlier, this carbon had shared these two electrons with this carbon, right? This carbon was sharing in the pi bond, it was sharing these two electrons with this carbon and this carbon. So now, after the shifting, now this carbon is rich. Why so? Because it has, earlier it had only 10 rupees, 10 rupees mine and 10 rupees of my friend. We are sharing it. Now, what my friend has done, he said, take my 10 rupees. Okay, now you will be rich. You will be electron rich. So it will be negative charge here. Understood? Understood? Now the electron, the neutrality of this compound has maintained. Right? We have maintained the electron neutrality. This was also overall neutral. This is also overall neutral. This is how we are going to make the resonating structures of double bond, single bond, lone pair. The trick is lone pair to double bond to negative charge. Lone pair to double bond to negative charge. Okay? Okay? Okay, bacha. Tell me, students, is this clear to everyone here? Is this clear to everyone here? Double bond, single bond, lone pair. That is, lone pair will be shifted to double bond and that double bond will be shifted to negative charge. This will be electron deficient and this will be electron rich. Right? Okay? Perfect. Now, where is your energy? Where is your energy? Where is your energy? Okay, now let us draw the structures of these three compounds, right? So this is CH2, this is CH, this is CH2, this is CH, this is CH2, this is CH. Now let us draw the resonating structures of these three. Let us draw the resonating structures of these three. Now what will happen here? It will have 6 lone pairs here, there will be 2 lone pairs here, there will be 1 lone pair here, right? Okay, the lone pair, then single bond, then double bond. Now what will happen here? Lone pair will be shifted to pi bond and this pi bond will be shifted to negative. Lone pair to pi bond to negative. Lone pair to pi bond to negative. What is the rhyme? Lone pair to pi bond to negative. What is the rhyme, bacha? Lone pair, nuclei will be in its own position. Nuclei will be in its own position. Nuclei, you will not change the position of nuclei and you will not change the position of sigma bonds. The only thing that we will change is pi bonds and lone pair. Lone pair will be shifted to pi bond, lone pair will be shifted to pi bond and pi bond will be shifted to negative charge. Because lone pair has shifted to pi bond, that's why it will be electron deficient. Electron deficient. And this is pi bond, this is electron rich. Shifted to here, then this is electron deficient and this is electron rich. Understood? A lone pair to pi bond to negative. Perfect. What is the reason? I have told you the reason. What is the reason? So see, when I have a negative charge here, then things will change. Okay. Usually students stuck here, they treat lone pair and negative charge as same thing. You are not going to treat lone pair and negative charge as same thing. This was, it had 20 rupees of its own. Now somebody has taken away your 20 rupees from you. Now what will you feel? You will be electron deficient. That is why there is positive charge. Now, if I talk about this thing, if I talk about another thing, that is double bond, single bond and negative charge. What will happen here? What will happen here? Understand, students? So what will happen here? This will be negative charge. Negative charge will be shifted to pi bond and pi bond will be shifted to negative charge. Okay, that is okay. Now, mostly students, what they do, what mistake they do like this. This is the pi bond, this is the sigma bond. Now this is fine now. Now, what they will do? They'll shift this negative charge to double bond. They'll shift this pi bond to negative charge and they will draw a positive charge here. They will draw this positive sign here. What is the reason? As I told you, negative charge means one electron of its own and one electron it has taken from somebody else, from some other atom, right? So, if you have 10 rupees of your own and 10 rupees from your friend, right? And now somebody has taken away your 20 rupees, your total 20 rupees. Now you will feel less deficient as compared to if those 20 rupees are your own only. This is the case of lone pair. This is the case of negative charge. In lone pair, you have 20 rupees of your own, right? And somebody has taken away from you. Then you will feel really, really sad. But in this case, you had 10 rupees and your friend had 10 rupees and your friend had taken 10 rupees from you, right? So that means you are better off, this case, it is worse. Like somebody has taken all your money. And in this case, you are sharing something. So now, in this case, you will be less electron deficient. And that is why here there will be no positive charge. Okay, there will be no positive charge. Let me make you understand again. So this electron, this negative charge means there's two electrons, right? One electron of its own and other electron of taken from someone else, right? These are the two electrons, right? And for lone pair, we had two electrons of its own, right? So now what happens here? In both the cases, they are shifted to pi bonds. Pi bonds means it is in sharing now. And this is also shifted to pi bond. And in this pi bond, here also it had one electron of its own. Here also, now this own electron is in its own place only. Now, if you have 10 rupees, your friend had 10 rupees and you are going to buy something of like, with those 20 rupees, you are going to buy one packet of Lays, right? So you're going to eat those Lays together. So in that way, you are not deficient. You are consuming those 10 rupees. Now, this carbon is also consuming its 10 rupees. This carbon is also consuming its electron. Earlier it was as a negative charge and now it is as a pi bond. But the carbon has its electron on its own place, right? Earlier it was negative charge and now it is in the form of pi bond. Understood? Understood or not? Understood or not? So guys, this is a very interesting thing, right? This is a very interesting thing. Students usually make mistakes in this. See, you have one lone pair here. You have one negative charge here. And this is double bond, this is double bond. What will happen here? In this case, you will have this carbon, this single bond, then this double bond. And now in this case, because the lone pair, both these electrons were its own, that's why it has now one electron. Okay. Now I am marking this as a pink color. The electrons are of its own, right? And now it is in the shared position, right? Now it has shared its two electrons with this carbon. Now it is feeling electron deficient. But in this case, it had one electron of its own and one electron was taken from somebody else, right? So now when it becomes a pi bond, again it has one electron of its own and one electron is shared among this carbon. Understood? And that is why there is no positive charge here. And it will be negative charge. Understood or not? Tell me. Will you make any mistake by doing the resonance of a lone pair and a negative charge? In lone pair, there will be electron deficiency, and in case of negative charge, there will be no electron deficiency. Reason I have told you. Okay? Understood, ma'am. Understood, ma'am. Understood, ma'am. Okay. I'm going to teach you again. The last time I'm repeating this. Right? See. This is the case. This is the case of lone pair. And this is the case of negative charge. This is the case of negative charge. As I told you before, lone pair has one electron, lone pair has both the electrons of its own, right? Okay. It is from its own shell. Okay. It has not borrowed those electrons from somebody else, right? So now what will happen here? You'll have, this is A, this is B, and this is C. This is lone pair and this is double bond. Again, this is A, this is B, and this is C. This is double bond, this is negative charge. Now, as these two electrons of carbon of this C atom, these two electrons are of C atom only. It has not borrowed these two electrons from anybody else. And that is why when we convert this lone pair to this pi bond, after the resonance, this carbon will have a deficiency. This carbon C will have a deficiency. Reason is, if you have 20 rupees and somebody has taken away those 20, if you had 20 rupees and your friend said, take 10 rupees with you and give me 10 rupees. Now you will be electron deficient, right? You had 20 rupees and your friend has taken 10 rupees, right? You have only now 10 rupees, right? So now what happens here? This is negative and this is, now what happens here? Now in this pi bond, you have two electrons, right? These two electrons are these two electrons. These two electrons are now shared in the pi bond. It has to share its own 20 rupees with its friend. Now it is feeling electron deficient. That is why there is positive charge. Now when it comes to negative charge, you have A, you have this B, and you have this C. Now what will happen here? This negative charge will be shifted here and this pi bond will be shifted here. Because of this pi bond, there will be negative. But now there will be no negative, mark my words, there will be no negative while you are shifting negative charge to pi bond. When you are shifting negative charge to pi bond, there will be no positive on the atom which was having negative charge before. What is the reason? Example is you had 10 rupees, your friend had 10 rupees, and you both were sharing those 10 rupees, right? But now what your friend did, he said, okay, earlier you thought, let us do one thing, I am going to buy one chocolate, This is what you thought. I have 10 rupees and my friend has 10 rupees, right? I am going to buy my own Kit Kat, he is also going to buy his own Kit Kat. Now what we both decided, why don't we combine these two 10 rupees and make this 20 rupees and buy something else of 20 rupees. Now, and share that thing among us. So now this is what they did, okay? They are now sharing those 20 rupees, right? But the condition is same. Even now, it is in the position of sharing only. That is why this carbon is not feeling electron deficient, and that is why there is no negative charge on it. And I hope so this is clear to you now. Okay? I really hope so this is clear to you now. Because this 10 rupees, 20 rupees thing is like, you can easily understand this, right? Right? Okay? Okay? Yeah, we will be doing questions. Don't worry, I'm here only. This is clear to you now? This is clear to you? Perfect. Okay. So now this is very easy. You have double bond, single bond and positive charge. What will happen here? You have double bond, single bond and positive charge. Very easy. This double bond will be shifted here. That's it. Okay. Now, what happened here? It was having one p orbital, one p orbital, one p orbital. Right? But this p orbital was empty. That is why it was having positive charge. This p orbital was having this half-filled and this was also half-filled. That is why there was sideways overlapping and hence this pi bond was there. Now, what happened? This electron got shifted from here to here. Right? This electron got shifted from here to here. Now, this carbon is now electron deficient, and that is why the resonating structures will be, this will be positive and this will be pi bond. Okay? Because now the overlapping is between these two atoms, and this is electron deficient. That is why this is positive and this is double bond. Understood? Understood? Now, let's see one more thing. You don't need to draw any orbitals while making resonating structures in exams. What you will do simply, just convert this. Just transfer this positive charge from first position to third position. From first position to third position, just transfer this positive charge. Okay? Just transfer this positive charge from first position to third position and transfer this double bond to the neighboring carbon atom. Okay? Right? Now, next is p bond when it is half filled, when it is in the form of a free radical. Here, homolytic cleavage will occur. Now, what is homolytic cleavage? If we have a bond like this, now, if the electronegativity difference is there, if B is more electronegative, then it will pull the electron to itself, and the cleavage will be A positive and B negative, because it has taken both the electrons. Homolytic cleavage means it does not have any electronegativity difference. So here, one electron will shift here, one electron will shift here, and this is Fisher arrow. Okay, so now this will be A free radical and B free radical. Understood? This will be A free radical and B free radical. This is homolytic cleavage, this is heterolytic cleavage. Homo means one, right? Clear to everyone? Now, let us understand what will happen in free radical. What will happen in free radical? Now, this carbon has p orbital, this has p orbital, this has p orbital, right? So, these both carbon atoms are forming pi bond. That means it will have one electron here, one electron here. And there is sideways overlapping between these two carbon atoms. And that is why pi bond is forming here, right? And this particular carbon is not empty. It has a p orbital which is half filled, right? Which is half filled. So now what will happen? Sometimes this carbon will form sideways overlapping with this carbon and hence this pi bond. And sometimes it will form pi bond. It will form form sideways overlapping with this other carbon atom, and hence this carbon atom will be alone. This carbon atom will have this dot, will have this free radical. Right? So the resonating structures will be same as carbocation, same as carbocation. Just shift this. Earlier you have shifted positive charge to first carbon to third carbon. Here you will shift the dot from first carbon to third carbon. Okay? So here you will draw it like this. Here you will draw it like this. CH2, single bond CH, CH2. Now this will be double bond and this will be free radical. What happened here? Very simple. This double bond has shifted here, and now these two are forming sideways overlapping and pi bond, and this is alone here, right? So actually this will be Fisher arrow. This double bond will have homolytic cleavage here. One electron will go here, one electron will be here, and this one electron and one electron will form pi bond here, right? Okay. Tell me, is this clear to everyone here? Here there will be homolytic cleavage, right? This pi bond will have homolytic cleavage, and that is why one electron will come on this carbon and one electron on this carbon, and that is why sideways overlapping will be occurring here, and hence pi bond will be formed here, right? Okay. Both atoms get one of the shared electrons. Yes, are reactive. Yeah, they are very reactive. They are very reactive. But you can consider free radical. You can draw the resonating structures of free radicals same as you draw the resonating structures of carbocation. Same way. There is no difference between this and this. There is no difference. Same way you can draw the resonating structures of free radical. Okay. Now next is I think we have done this. This is done. Now let us draw the resonating structures of second case. We have covered first phase, that is double bond, single bond and p orbital. We have discussed fully filled, half filled, vacant, everything. Now what we are going to do now? Alternate double bonds. Alternate double bonds means double bond, single bond, double bond. Now what will happen here? Let us understand that. Now what we are going to do? This double bond will be shifted here, and this double bond will be shifted here. Right? And how will you draw it? How will you draw it? This is CH2, single bond CH, single bond CH, single bond CH2. The trick to draw resonating structures is that never change the sigma bonds and nuclei. Just firstly draw the sigma bonds and the nuclei. After that, change the unshared electrons or lone pair electrons or pi electrons. Okay. So now this pi electron is shifting to this position. That means there is this one double bond here, right? And this double bond is shifting. The pi electrons of this double bond is shifting from here to this carbon. That means there will be one negative charge over there, right? So this will be formed. Now, but the electrical neutrality is not maintained here. This whole molecule is positive and this is negative. How is this possible? Because now this carbon atom had 2 electrons as a shared pair, right? And these 2 electrons have shifted from here to this position. Now this carbon atom will feel electron deficient. It will be electron deficient because earlier it had 10 rupees of its own, but now somebody has taken its own 10 rupees from itself. Like you have some clever friend who said, okay, give me your 10 rupees, and he went to canteen and he bought something from himself and his girlfriend or boyfriend, whatever, and they are eating it together, and you are alone there sitting. Now this is the case of this carbon. This carbon, he take away its 10 rupees, its money, and now he's eating with his own friends, not with this carbon. Now this carbon is feeling alone, and that is why there is positive charge on this carbon, right? Okay. So now electrical neutrality is maintained. There is one pi bond, there are positive, negative, which means that is neutral. This is also neutral, this is also neutral. Okay? Yeah, you can definitely watch these lectures. Okay? Yeah, the explanation is better, but I'm feeling like I want to express myself more, but because of this language barrier, I'm not able to express that much. But you know, I'll improve. I will improve. Poor carbon, yeah, poor carbon. Otherwise, in Hindi, I take very funny examples. Okay, I take very funny examples. But now, I am, when you have to speak some language that you are not used to of speaking, you have to think in your mind, okay, how do I call this particular thing in English? What do I call this thing in English? I have to think and then deliver that example to you. That part is little tricky, but yeah, I'm trying my best, okay? I'm trying my best. So tell me if you're understanding that or not. Okay? Yeah. No, I'm very much comfortable. If, in fact, I'm learning little Malayalam words from Gopika ma'am, right? Just to understand you better. Yes. Okay. So, have you understood the lecture till now? Have you understood? Let's grow and improve together, ma'am. Yes. High five. High five. Give me high five. Everyone, give me high five. Everyone, give me high five. You know now ritual of the class. You're going to teach me one Malayalam. It's Malayali or it's Malayalam. Firstly, teach me that. If I apologize, if I'm speaking anything wrong, if I'm pronouncing anything wrong, I'm so sorry. In your language, it's I'm in advance only. I'm apologizing for that. Okay, tell me it's Malayalam. Okay, some Malayalam. Okay, yeah. So I learned one new word that was uh, wait a minute, that was Sugamanu, right? Sugamanu. Is it? Actually, I have proper notes for that. I actually have proper notes for my Malayalam words. Okay, let me see. That was Sugamanu. Yeah, that was Sugamanu. Yeah, I have proper notes for that, bacha. I have proper notes. Malayali is the person speaking Malayalam. Okay, perfect. So I'll be a Malayali soon. I don't know if I'll be able to, understand it well, but I'm trying my best. I like speaking new languages, but I'm so dumb when it comes to languages. Like learning new languages is a tough task for me. I know how to understand chemistry, but when it comes to languages, I'm little on the downside. Okay? Yes. So, okay, somebody is teaching me some new word. That is the end of this lecture. You will teach me some new word of Malayalam in the end of this lecture. Okay? Okay? Now, namaskaram in Kannada. Yes. Okay, that is namaskaram. Okay. Yes, sugamanu. Yes. Okay. Perfect. I'm loving this already. In the end of this session, we will do, because there are so many things left right now. Let's jump to the topic again. Okay. alternate double and single bonds, alternate double and single bonds. So what is the name of this compound? This is propanol. This is propanol. This is also called acrolein. This is also called acrolein. Okay, this is also called acrolein. Now you have two lone pairs here also, right? So what will happen here? What will happen here? This is double bond, single bond, double bond. The resonance is double bond, single bond, double bond. So what will happen here? This is more electron negative. So it will pull the electrons towards itself, and this double bond will be shifted here, right? So the resonating structure will be, this will be negative, this will double bond here, and this will be positive, right? So were you able to draw the resonating structures? From where the double bond has taken out, you have taken out the double bond from this carbon. Now this carbon will be electron deficient, and this carbon, between these two carbon, you will have a new pi bond, right? And this oxygen will pull the electrons from this pi bond, so it will be electron rich. Okay, right? So were you able to draw the resonating structures? Right? Okay. Okay. Are you able to draw? Are you able to draw the resonating structures here? Bacha, I'll definitely learn your language. Don't worry. Love the diversity of India. Right? So now, bacha, next is, you understand bacha? Do you understand bacha? That is my natural accent. I can change that to students. So, you know, I find speaking students very tough. So, I say bacha to my students. So, do you understand bacha? Bacha means my little kids. Okay? So, it's very natural. It comes very naturally to me. I'll say bacha. Okay? Understood? Okay. So, now this is positive and this is lone pair. Now, here there is no double bond. There is no alternate double bond, single bond. There is no double bond, single bond, p orbital. Here we can see positive, that means vacant orbital, single bond, and one lone pair. Now, for example, you have 100 rupees and your friend, for example, you have lunch. You are having lunch also. Your mom has prepared lunch for you. Tasty dosa, right? I love dosa, by the way. Okay. So you have lunch, and also you have 30 rupees with you, right? So now your friend, he has not bought any lunch from home, and he also don't have any money. So now what will happen? He's very electron deficient, like this carbon. He don't have money, he don't have lunch box. Now what will happen? You don't have lunch box, no money. This is very electron deficient. This is electron rich. This nitrogen has lunch box, and this nitrogen has money as well. Now this is electron rich. What you will do? You will give either your lunch box or you will give your money to your friend. Right? Are you that much concerned about your friend? Right? No. Sharing is caring. Perfect. Sharing is caring. Okay. So now what will happen here? It will donate its one lone pair here. Right? So what will happen? The resonating structure will be CH2 double bond NH2. And it itself will feel electron deficient because it had money, it had lunchbox. Now it is donating or giving or sharing that with his friend. Now what will happen here? That particular nitrogen will feel electron deficient. Okay? That will feel electron deficient. Or you can easily say, if nitrogen is forming, the trick to learn is, if nitrogen is forming 3 bonds, it is neutral. It is neutral. If nitrogen is forming 4 bonds, it will have positive charge. If nitrogen is forming 2 bonds, it will have a negative charge. For every atom, it is true. If you're expected to have 95, if you think that you can crack 95 out of 100, right? And you are cracking 99 out of 100. So what you will be feel very positive, right? So that is happening here. It thought it will form 3 bonds, but now it is forming 4 bonds. That is why it is positive. Now, if you thought you will have 95, but now when the result came, you have only 85 marks. Now, what will happen? You will feel negative. Same way. Okay? Just a very funny way to learn this. Okay? Just a way to learn this. Just a way to learn this. Okay? There's no as such logic behind that. Okay? Got it? Now, next is, this is called back bonding. Now this oxygen is also electron rich. This oxygen is also electron rich and this is electron deficient. What will happen? This will donate its electron here and it will form CH2 double bond OH. Now oxygen is supposed to form 2 bonds, but now it is forming 3 bonds. That means it is feeling very positive. Okay, it is forming more bond than that was expected out of it, right? So it will be positive here. Understood? Understood? Earlier we thought it will form 2 bonds only, right? But now it is forming 3 bonds, more than what was expected from this oxygen. So it will be very positive. Okay, perfect. Now next is practice. Now let us do some practice questions here. Let us do some practice questions. Take out your notebook and draw these structures with me. This lone pair, this oxygen has 2 lone pair. This oxygen has 2 lone pair. But which will form a resonance? For resonance, you need to have the conditions of resonance. That is either alternate double bond, single bond, or there should be back bonding, or there should be double bond, single bond, and a p orbital. Now, what does it have? It does not have alternate double bond and single bond. It does not have any atom which is electron deficient, right? So no back bonding here. Here we can find double bond, single bond, and lone pair, and that is why double bond, single bond, and lone pair resonance will occur here. And that means this lone pair will be shifted here, and this pi bond will be shifted here, and hence the structure will be, this will be O negative, and this will be double bond, right? This will be double bond, yeah, and this will be positive here. Okay, this will be positive here. Understood? Understood, everyone? Have you drawn this structure? Have you drawn this structure only? This is the arrow that we use to represent. This is the arrow that we use to represent 2 structures or 3 structures. Okay, that this structure is getting converted into this structure. Now, if we have to draw the resonating structure, then we draw these 3 lines to represent resonance hybrid. Okay. Tell me, have you drawn this structure? Yes? Yes? Is everybody able to draw this structure? Is everybody here able to draw these structures? Right? Okay? You need to focus on the session. Otherwise, focusing on me will not give you any rank. Okay? Yeah. And I am not here for that. For that matter, right? Okay. So now let us see what kind of resonance is present here, right? Now it has lone pair, single bond, double bond. Lone pair, single bond, double bond. And here it is double bond, single bond, vacant orbital. It has 2 resonance present here, right? So what can we do? We can do one thing here, right? Let us draw the resonating structure. Firstly, let us focus on this resonance. Firstly, let us focus on this conjugation, okay? So this pi bond will get shifted here. Okay. If you have double bond, single bond, vacant orbital, what you do? You shift this cation from first to third position, right? You shift this cation from first to third position. From first to third position. So I am shifting this cation from first to third position, and I am shifting this pi bond to this position. Right? This is the resonating structure. Now, let us draw another resonating structure. That is, let us shift this lone pair from here to this. What is this? What is this? What kind of resonance is this? Tell me, what kind of resonance is this? This is called back bonding. It has excessive, it is electron rich, and this is electron deficient, and this is called back bonding, right? So what will happen here? What will happen here? The resonating structure will be NH2, and this is double bond, or I can write it as NH2, and this is double bond. This is CH, this is CH, this is double bond, CH, and this is CH3. Right? Okay. This pi bond has shifted, this lone pair have shifted here, so it will feel electron deficient. And now this was electron deficient, and now it has a pi bond. Now this will not carry any positive charge, right? Because it has fulfilled its deficiency. It has now 1, 2, 3, 4 pi bonds, 4 sigma bonds only. Tetravalency is completed here, right? Okay. Okay, so these are the three resonating structures. These are the three resonating structures, right? Clear to everyone here? Is this clear to everyone here? Have you were you able to draw these structures? Were you able to draw these structures? When the topic will end, the session will end. Okay. The moment topic will end, session will end. Okay. Now A, B, and C. Tell me out of these A, B, C, where resonance will be present. Out of A, B, C, where resonance will be present. This is A, this is B, this is C. Out of these, where resonance will be present. Right? First is, this is electron rich. And students, we have this sulfur atom here. Sulfur is electron deficient. Okay, sulfur is electron deficient, and that is why this electron rich electrons can shift from this to this, right? From here to here. Okay, also from here to here, and that is why it will show resonance by back bonding. Here we have boron. We know the octet of boron is not complete. We know this from inorganic chemistry, right? And that is why this is electron deficient and this is electron rich. So there will be back bonding. In this case, we all know chlorine has six lone pairs. 3 lone pairs, 6 lone pair electrons, right? But chlorine also have vacant d orbitals. Right? Chlorine also have vacant d orbitals, and that is the reason this electron rich carbon will donate its electrons to chlorine, because chlorine has vacant d orbitals. Okay? It has vacant d orbitals. Understood? Understood or not? So these all will show back bonding, and these all will show resonance through back bonding. Understood? Understood? Shall we move? Okay, shall we move? Okay. Now, next is this question. Let us draw the resonating structures. Students, let us draw the resonating structures. Along with me, draw the resonating structures, guys. Let us draw the resonating structures. What are the resonating structures? So let us draw that. This is double bond, single bond, lone pair. That means this lone pair will be shifted here and this pi bond will be shifted here. So the resonating structure will be this oxygen. This is double bond and this is negative, right? And this lone pair if lone pair is getting converted into pi bond, then there will be one positive charge here, right? There will be one positive charge. Okay, so this is the resonating structure. This is the resonating structure. There will be only one more resonating structure possible here, right? Ma'am, shall we draw resonating structure of 3 previous slides? You can draw that. You can draw that. Okay? That's your homework. Draw the resonating structure of previous slides. Okay? Understood? Yes. Now, let us move. How will you draw the resonating structures here? You have one lone pair here. You have two lone pair here. So, what is the resonance present here? This is one double bond, single bond and lone pair. Right? Do not consider this lone pair in resonance. It cannot participate in resonance. Only this can participate in resonance because the condition is double bond, single bond and lone pair. Not double bond, lone pair. This is not the condition. Okay? So these lone pair will participate in the resonance. So the condition will be this will shifted here, this will be shifted here, and hence the structure will be CO negative, and this is double bond NH2, and there will be positive. Understood? Understood? Have you drawn the structures? Are you able to draw the structures? Are you able to, guys? Please Tell me, are you able to draw the resonating structures or not? Are you able to draw the resonating structures? Perfect. Perfect. Okay. So now let us see, out of these A, B, C, D, E, F, G. Okay, I have done my homework here. Okay, I have done my homework here. So just to save the time, I have written the structures before itself, so that we can save the time in the class, right? Okay. So now, which I have already taught back bonding. I've already taught back bonding. After this, I'll recap back bonding for you. Okay. So now you have 1, 2, 3, 4, 5. You have these 1, 4, 7 structures. You have to tell me yes or no. Out of these, which of the following will show resonance? Answer this in the comment section. Out of these, which of the following will show resonance? Right? A, B, C will show resonance, C, D, E will show resonance, E, F, G will show resonance. Out of these, which of the following will show resonance? Tell how many resonating structures are possible. After drawing the resonating structures only, you can tell. There is no trick to that. Okay? There is no as such formula or trick to how to calculate the resonating structures. You have to draw the resonating structures. Okay? Perfect? Perfect. So now B, D, E, F is one answer that is coming. What else, students? Only one student have answered. One student saying B is showing resonance. B, D, E, F is showing resonance. And what else? B, E, F is showing resonance. Amulya has Amulya, Suresh, then Sanvi, Sarath, Shivani, Nancy, Archit. Perfect. Perfect. Shishadri. But if I am pronouncing anyone's name incorrectly, I am so sorry about it. Okay? Yes. Perfect. Perfect. So now let us see. Let us see. Let us see. So this is double bond, single bond, single bond. The resonance is not present here. There should be double bond, single bond, double bond. But it is not alternate double bond and single bond. So there is no resonance. Right? This is double bond, single bond, and lone pair. So that is why it will show resonance. This is only double bond, one double bond present here. No other double bond. There is no back bonding. There is no p orbital here. So it will not show any resonance. This is double bond, single bond, and p orbital. And that too, it is filled p orbital. So it will show resonance. This is double bond, single bond, and then p orbital. There are two single bonds between p orbital and double bond. But we should have only one single bond or sigma bond between double bond and negative charge. So this is not possible. This is phenylketine. This is a very unstable cation. So resonance is not possible here. Okay, this is a very unstable cation. Very unstable cation. Right? So there is no double bond. There is only one free radical. Here also it is not possible. So the answer is B, D. That's it. B and D are showing resonance. Rest all are not showing resonance. Only B, D. Even F is not showing resonance. This is phenylketine, which is very unstable cation. Okay? F is not showing resonance. Okay? Okay? Yes. Shishadri is saying pronunciation is correct, ma'am. Perfect. Okay. You know what happens if someone by mistake says it's hi Diksha? I'm like, it's not Diksha, it's Diksha. Okay? So sometimes we don't like, most of the people don't like somebody else pronouncing their name incorrectly or writing their name incorrectly, right? Because it's our name, yeah? It's our name. That's why I said, if I'm pronouncing anyone's name incorrectly, do let me know. Now, till now is everything clear to all? Right? So now let us find. So one of the students asked, ma'am, what is back bonding? So bacha, if you have one A and one B, right? If this is electron deficient, for example, it has positive charge. This is electron rich. So now it will donate the electron. Electron rich will donate the electron to electron deficient. That is called back bonding. That is called back bonding. Right? Okay? There can also be another case if B has vacant orbitals, it has vacant orbitals, right? Vacant d orbitals, and this is having negative charge, then also it is donating the electrons. Okay, this is called back bonding, right? So now let us understand the stability of resonating structures. Shall we understand the stabilities of resonating structures? Very easy. We know how to draw resonating structures. There are few conditions to draw resonating structures. I'm sure if you know those three conditions, there are three conditions. Let me recap it for you. Let me summarize this for you. First condition was double bond, single bond, p orbital. That can be negative. That p orbital can be a free radical. Then p orbital can be a positive. That p orbital can be a lone pair. This is the first condition of resonance. Second condition is alternate double bond, single bond. Triple bond are not in your syllabus. Third condition is back bonding. Third condition is back bonding. You need to understand these three conditions. You have to find these three conditions. If you can find these three conditions, then resonance will be there. If you are not able to find these three conditions, there will be no resonance. Okay, understood? Because it has positive, yes, positive, yes. Now, why doesn't phenylketone also show resonance? So, guys, what happens in this phenylketone, you have what? See, you have this double bond, single bond, double bond. There is one positive charge on this electron. So now, what is happening here? The pi electrons are revolving. The pi electrons are revolving throughout. The pi electrons are revolving throughout in this bond. It are revolving. So that is why this positive charge directly on a carbon in which delocalization is there, and that is why it is not stable. Okay, that is why it is not stable. Moreover, how can resonance occur here? There is, if you can draw it like this, if you can draw it, double bond, double bond, double bond. This is double bond positive and this. What I told you, there should be double bond, single bond, and then positive. I can't see any condition like that. And this positive has again a double bond on its own atom. And that is why this thing is making it unstable. Okay. There are two pi bonds and there is this positive charge. That means there is this electron deficiency there. And that won't be stable because it already has pi electrons revolving in this ring. So how can electron deficiency be stable on that? Okay. Understood? And that is why phenylketone is not a stable cation. It is the most unstable cation. Okay? Most unstable cation. Right? Ma'am, negative charge having lone pair also show resonance. I didn't understand you. Negative charge having lone pair. What do you mean by that? Can you give me an example of that? Okay, so now stability of resonating structures. We need to know certain rules of how we will define the stability of resonating structures. So first is neutral is always, if you can find a resonating structure which is neutral, that is always more stable than charged one. Okay, neutral is always more stable than charged one. This is amazing. The question will be really amazing, right? Neutral will be always more stable than charged one. Second is stability. If, for example, you are not able to find any neutral structure, all the structures are charged only. Now, how to define which is more stable? Now, calculate the number of pi bonds here. Okay, more the number of pi bonds, more will be the stability of that structure. Firstly, find out if there is any neutral structure. If there is neutral structure, that will be the most stable structure. If you can't find any neutral structure, all of them are charged, then find the number of pi bonds. More the number of pi bonds, more will be the stability. Now, third is negative charge on more stable atom. That is more stable. Negative charge is more stable on which thing? If we go along the period, negative charge stability increases. Down the group, negative charge stability increases. What do you mean by that? See, along the period, due to electronegativity, stability increases. And down the group, due to size, due to increasing size, stability of negative charge increases. This is very important. along the period and down the group, negative charge stability increases. Along the group, due to increase in electronegativity, stability of negative charge increases. Here electronegativity dominates. But down the group, size of that atom dominates, and more the size of atom, more is the stability of negative charge. Right? More the size, more is the stability of, because it can accommodate easily in larger size. Okay? Understood? Yes. Perfect. Have you understood this point? Have you understood this point? Yes, we'll draw resonating structures of phenols as well. Now, next is more charge separation, less stability. Now, we will understand this. Now, let us understand this. What do you mean by more charge separation? For example, I have a compound. I have two resonating structures. This is the charge separation, positive and negative in the same compound. And this is another resonating structure where this is positive and this is negative. Now, this is less charge separation. Positive and negative are at less distance. There is less charge separation and there is more charge separation in the second structure. And that is why we say more the charge separation, less is the stability. What we need, less stability, more the charge separation, it means that this will be more stable than this. Okay? If we find out that there are just two resonating structures left which have just difference of charge separation. Now, the lesser is the charge separation, more will be the stability of that structure. Understood? Understood? Understood, right? Okay. So now let us do some examples. And you will have a better understanding after doing the examples. Right? Okay. So let me see how many of you give the right answer. Let me see. How many of you are giving the right answer. I want the right answer. Yes, let me see. So here you have, here it is negative charge on, see, there is no neutral. First thing that you need to know, is there any compound, any resonating structure that is neutral? Both the resonating structures are charged. That means first we can skip it. Okay. Second is calculate the number of pi bonds. Okay. This is one pi bond. Here also we have one pi bond. That means we can also skip that. Now, third is negative charge is more stable along the period and down the group. So now the negative charge is on oxygen atom. Here the negative charge is on sulfur atom. And we know down the group is OSSCTEPO. This is down the group. So negative charge is more stable on sulfur atom. Negative charge is more stable down the group. It is more stable on sulfur atom. And that is why this is more stable than this. So B is more stable than A. Perfect. Everyone has answered B. Very good. Very good. Everyone has answered B. Perfect. Now, let us do another. This is A, this is B, this is C, and this is D. Now tell me, out of these, can you find any structure which is neutral? Right? What will be the answer? Which will be the most stable resonating structure out of these? There is no neutral atom here. You can't find any neutral atom here. Right? Neutral structure here. Right? So that is why. Now let us calculate the number of pi bonds. Here we have one pi bond. Here we have two pi bond. Here we have one pi bond. Here we have one pi bond. And that is the reason B is the most stable resonating structure here. B is the most stable resonating structure here. Right? After that, let us see. After that, let us calculate another. No, I think that is it. B is the most stable resonating structure. Now, this is A, this is B, and this is C. Tell me which of the following is the most stable resonating structure here. Which of the following is the most stable resonating structure present here? Firstly, let us see out of these which is neutral. Can you find any resonating structure that is neutral? Yes, I can easily see that. A is neutral. This is charged and this is also charged. And that is why A is the most stable resonating structure here. A is the most stable resonating structure here. Okay? A is the most stable. Somebody is saying that B has more pi bonds. Firstly, understand, the first point is to know which is neutral. If there is no neutral resonating structure, then jump to number of pi bonds. Okay? This is the sequence that you have to follow. Firstly, see neutral, then see pi bonds, then see negative charge, then see charge separation. This is the sequence that you need to follow. Okay? Now between these two, which is more stable? This is 4 pi bonds and this is 3 pi bonds. So that is why A, then B, and then C. Right? This is the stability order. This is the stability order. No, guys, we are dead and we are now. I'm having this session from heaven. Okay. Now, this is A, this is B, this is C, this is D. Tell me which is the most stable resonating structures. Okay? Which is the most stable resonating structures? Yes, these are very interesting. Which of the following is the most stable resonating structure out of these? Which is neutral? You can easily see. A is neutral. A is neutral. So it is the most stable resonating structure. After this, let me calculate. After this, what is the stability order? Now let me see. This is the most stable. Now these three are charged, right? Let us calculate the number of pi bonds. Here there is no pi bond, it has one pi bond. That is why A, then B. Now I have to calculate between C and D. There is no pi bond in this. Let us see where the negative charge is stable, right? Negative charge is present on more electronegative atom. Negative charge is present on less electronegative atom. And negative charge is more stable on more electronegative atom. And that is why C, that is why after B there will be C and there will be D. Right? This is the order of stability here. Right? Yes. Okay, this is the order of stability here. Thank you. Yes. Okay, perfect. Now, let us move. A, and this is B, this is C, and this is D. Out of the following, which is neutral? Out of the following, which is neutral? Can you find any structure that is neutral? Tell me, let me see. How many of you can find out the most stable resonating structure out of this? Let me see. Let's see. Out of these students that are watching this live right now, how many of you can answer this question correctly? A, B, C, D, somebody has said A, then B, then C, then D. You should definitely watch this if you're in class 11th or 12th. Both should watch this video. This is very important for you. This is GOC, most important for any student, even if you are preparing for boards, you are preparing for NEET. For boards, this will be too much for you. Like this will be too much for boards. But for NEET, for JEE, you should watch this video. Okay. Now, yes. All the students are saying A, then all the rest of the students are saying C. Somebody is saying DCB. Okay, let us see. Firstly, can you find any neutral structure here? No, I can't find any neutral structure here. Now, what I will do here, I will find out the number of pi bonds. This is 3 pi bonds. Here are 1, 2, 3 pi bonds. Here are 1, 2, 3 pi bonds. And here also we have 3 pi bonds. So the pi bonds are also same. Now what to do? Let us find out the negative charge here. Negative charge is more stable on which atom? Right? The negative charge here is present on carbon. Here it is present on carbon. Here it is present on chlorine. And here also it is present on carbon. That means here the negative charge is most stable. Negative charge is stable on more electronegative atoms. So C is the correct answer. C is the correct answer. Perfect. Done this? Have you done this? Perfect. We can't differentiate between A, B and D. They are not equivalent. I won't say they are equivalent. They are not equivalent. But yes, on the basis of these rules, we can't differentiate. We can only find out the most stable out of these. Right? Okay. Now, what is the answer to this? A, B, C and D. Let me see how many of you can give the correct answer here. How many of you can give the correct answer here? Right? Firstly, let me see if there is any neutral resonating structure present here. If there is any neutral resonating structure present here. If there is any neutral resonating structure present here, let me see how many of you can answer this correctly. Have you all liked the session? Have you all liked the session? Is it or not? If you like what I am teaching, also like the session and do comment down your feedback and all the question or the homework. Do comment down. Okay. Now A is more pi bonds. Now there is no neutral structure here. Then after that, let's jump to calculating the number of pi bonds. This is 2 pi bonds. Here we have 1 pi bond. Here we have 1 pi bond. Here also we have 1 pi bond. That means this is the most stable structure. This is the most stable structure. A is the most stable structure of this, right? A is the most stable structure. Now after that, if I have to calculate, no, you will need to, right? Okay, A is the most stable structure present here, right? Is it? Yes. Now let us calculate. We are done with the questions. Now let us jump to another topic. Is everything clear to you till now? We know the rules of resonating structure, how to draw resonating structures. Now we know the rules of calculating the most stable structure out of all the resonating structure that are given to you. Okay, these two topics we have finished. Now there are just little topics left. We will do that in another half an hour. Okay, perfect, perfect. Clear to everyone here? Is this clear to everyone present here? Yes, ma'am. Perfect. Very good. Very good. I'm so happy for you all. So now let us calculate the charge on resonance hybrid. How to draw resonance hybrid, ma'am? Okay, let us draw the resonance hybrid first. Now, let us draw the resonance hybrid. This is double bond, this is single bond, and this is negative. So this negative will be converted into pi bond, and this pi bond will be converted into one negative. And the resonating structure will be C O negative, double bond O, and this will be O negative. Now, if it has shifted like this negative bond has shifted to pi bond, and this pi bond has shifted to negative charge, then the resonating structure will be C O negative, double bond O, and this is O negative. Have you drawn these resonating structures? Have you drawn these resonating structures? Yes, perfect. Now, let us draw the resonance hybrid here. For resonance hybrid, firstly draw the nuclei as it is. This is draw the nuclei and sigma bonds as it is. Okay, this is the oxygen, sigma bond oxygen. Now, let us draw the double bond, right? As the double bond is also present here, so let us draw it by dotted line. The double bond is also present here. Let us draw it by dotted line. The double bond is also present here. Let us draw it by dotted line. Okay. Array. This array comes very naturally to me. Like Gopika ma'am says, Ayyo. This array comes naturally to me. Okay. So now, this is the structure. Now, either you can, now the trick is how to calculate the charge on resonance hybrid. This is the resonance hybrid. Either you can simply draw it like this minus delta. This delta means partial negative charge is present here. Some of the negative charge is distributed on this oxygen and this oxygen. That means delta negative. Or you can actually calculate the exact negative charge here. That will be calculated by minus how many atoms? Okay, how much negative charge is present here? Negative. That means total negative charge is -2. So let us draw here -2. -2, I have written -2. And this -2 charge has distributed in 3 atoms. This -2 charge is distributed among 3 atoms, right? 3 atoms. Yes, it's like ozone. Yes, perfect. Ozone is also another example of this, right? So this is -2/3. So this will be -2/3, -2/3, -2/3. Perfect. Yes, this is the formal charge. Perfect. Very good. You have done it in inorganic chemistry as well, right? You have done it in inorganic chemistry as well. Chemical bonding and organic chemistry are somewhat related to each other. They help each other a lot. Okay. For GOC, chemical bonding is the base of GOC, right? Okay. Perfect. So moving to next. What are equivalent structures? Can anybody please tell me what are equivalent structures? What are equivalent structures? Can anybody please tell me? Start, Nancy, Shashna, then Abhitha. Who else is present here? Sanvi, Bikram. Tell me. Bonding is my favorite. Yeah, that was my favorite also. Chemical bonding is one of my favorite chapters also. Right? Okay. So tell me, everyone present here, tell me what do you mean by equivalent structures? What do you mean by equivalent structures? What are equivalent structures? Equivalent structures which have same resonating structures that are equal and they are of equal energies. Okay, equal energies and equal stabilities. So now, if I have to draw the resonating structures, this is double bond, single bond, vacant orbital. This will be shifted here. This will be shifted here, right? And the resonating structure will be double bond and this will be positive here. Right? If I have to draw another resonating structure, this will be shifted here and there will be resonating structure as double bond. This will be positive. So, if we can see, all these 3 structures are actually same. All these 3 structures are actually kind of same only. They have same energy. So, what I will be writing? These are equivalent structures, right? These are equivalent structures. As you can see, this is also equivalent structure. They also have same energy, right? This is also equivalent structure. Understood? Understood or not? Understood or not? Next is cross and extended conjugation. Next is cross and extended conjugation. Right? Yes, 3 structures. Very good. Very good. Dancing resonance is not here. I'll teach you dancing resonance. I'll definitely teach you dancing resonance. Yes. Shishadri. Very good. Dancing resonance. I'll do that. Yes. Definitely we are going to do that. Okay. When we will do stability of carbocation, we will understand dancing resonance, which actually is the deciding factor. If there is dancing resonance, the stability will be maximum. Right? Okay? Yes, perfect. So now, cross and extended conjugation. What is cross and extended conjugation? For example, you have a structure like this. You have a structure like this, right? And you have another structure. You have another structure like this. You have another structure like this. This is positive. This is double bond, and this is double bond. So now, extended conjugation is something that is in one direction only, right? That is in one direction only. Someone is saying, break, please, ma'am. I'm not going to give you break. No break. No break. You can eat, yeah. You can listen to the lecture and eat as well. I'm the one who is standing here. Okay? Just few things left. Why would I give you break for 15 minutes, bacha? Why would I break you for another 15 minutes? You'll have break for 5 minutes and you only study for the next 15 to 20 minutes. What's the point then, right? Let us complete that, okay? Let us complete that, okay? Okay. Now here is some person who is actually here for time pass. This person is here for time pass. Chal. Okay. He needs break till 12. Till 12 he needs break. Wow. Shabash. Shabash is like well done. So impressed. Okay. So now this is positive single bond, double bond, then single bond. So there are two structures. Here what will happen? This double bond will be shifted here. This double bond will be shifted here. There is resonance in one direction only. And here it is, this double bond can shift from here to here. This pi electrons can shift from here to here. Okay. So here is shifting of electrons in two directions. It can either take from this side, pi electrons can either shift from this side or shift from this side. Right? So this is cross conjugation. They are crossing each other. And this is extended. This is getting extended. So this is called extended conjugation. Now tell me which is more stable. Which is more stable? Is cross conjugation more stable or extended conjugation more stable? Okay. And any tricks to find bond between them? Bond between, there's not as the tricks to find bond between which? Like to draw resonating structures or what? Okay. I'll teach you dancing resonance when we are doing stability of carbocation and we're doing rearrangement of carbocation, hydride shift, methyl shift. In that, I'll teach you dancing resonance. Okay. We'll have a lot of question based on it. Done? Perfect. So, extended is more stable because this is only in one direction. If you are preparing for NEET and you are preparing from NCERT, you have full dedication for NCERT. We always say, teachers always say one thing to you. Just pick one book and study thoroughly. Okay? Just pick one book. Taking references of 10 books, n number of books, and you are taking references from n number of books, and you are studying from n number of books, and now even then you are just completing one book and then taking another book and completing another book, taking another book and completing that book also. In that way, you will mess up everything. That's why we say extended conjugation is more stable. If you are going in one direction, you are totally concentrated on that one direction, then you will be more stable. Then you are going here and there, then you will be less stable. That is why extended is more stable and cross is less stable. Right? This is a life lesson to you. That's why be extended, don't be cross. Okay? Okay? Yes. Okay, perfect. Now we have resonance and mesomeric effect. Can anybody please tell me what is the difference between resonance and mesomeric effect? There is just slight difference between resonance and mesomeric effect. There's just one difference between resonance and mesomeric effect. Let us understand what is that difference between resonance and mesomeric effect. So see guys, if you have this benzene, right? This is the benzene, right? So this is showing resonance. It does not need any external group so that it can do that resonance. It can delocalize its electrons. It does not need any external group. Now, if there is OH group on it, now what will happen? In this case, the lone pairs will be shifted here and this pi bond will be shifted here and the resonance will happen according to this OH group. Now, this is mesomeric effect, right? Now, if you have something like this, here it is just resonance. This is resonance. If you have something like this, this is just resonance. These are resonance. These are not mesomeric effect. These are not mesomeric effect. But if you draw something like this, benzene, this is resonance. But if you draw something like phenol, like you have OH over benzene, now the resonance will occur from this lone pair, right? Now this is mesomeric effect. So what can we say? Can we say? So we can say all mesomeric effects are resonance. This is mesomeric. We can say mesomeric is a sub part of resonance, right? For example, organic chemistry is a sub part of chemistry. Physical chemistry is a sub part of chemistry. In that way only, resonance, mesomeric effect is a sub part of, it is a type of resonance. Okay, when we have resonance because of some external group, that is called mesomeric effect, and that is why all mesomeric effects are resonance. All mesomeric effects are resonance only, but all the resonance are not mesomeric effect. This is resonance. This is resonance. But this is not mesomeric effect. This is resonance, but this is not mesomeric. This is resonance, this is not mesomeric. Because the resonance is happening because of double bond or vacant p orbital, not because of some other external group present on it. Okay? Okay? Understood? Don't spam, guys. Don't spam, guys. You're not making, this is not a fun game. Okay? This is not a fun game. This is about someone's life, right? This is about some student's life. They are contributing their time to this live session. So please respect that, okay? Don't spam here, okay? It's not about me, it's about those students who are giving their precious time to us, okay? So yes, for your friends, for your classmates, for somebody who is like studying till now, it's 10:15, they are watching this live and they want to improve their organic chemistry. Don't spoil this thing for them, okay? If you want to have fun, if you want to have time pass, go and watch some YouTube videos, watch stand-up comedies, do anything, okay? But don't come here and spoil their time, okay? Yeah, chalo. Now, this is plus m and this is minus m. Plus m and minus m. Now let us understand what is plus m and what is minus m. This is very important. When we are going to do reactions, then when we will do electrophilic substitution, nucleophilic substitution, these things are going to help you a lot when we will do directive influence. This will when you will do reactions, you will have to find the product. Where will this be an ortho product? Will this be a para product? Will this be a meta product? These things are going to help you. Okay, so understand this very carefully. Okay. Perfect, perfect, Sami. I'm so happy. I'm so happy that you are finding the organic chemistry interesting now. I'm so happy with that. So now this is plus M effect. Plus M effect means donation of electron. Like plus psi effect was donation of electron, plus M is also donation of electron. They are donating the electrons here. Okay, so now as they are donating the electrons, so let us see how they will donate the electrons. You have two lone pairs over this oxygen atom, is it? So let us draw this is phenol. Okay, let us draw the resonating structures of phenol. Everyone along with me draw the resonating structures of phenol and tell me, are you able to draw all the resonating structures correctly or not? Okay, let us draw these structures. Come on. Okay, so now what I'm going to do, I'm going to shift these lone pairs here and this pi bond here. Right? So this will be the benzene ring here, and this is the ring here, and this is double bond intact. This is also intact. This pi bond will be shifted to here. So this will be negative charge. This is sigma bond, and this lone pair will be shifted to 1 pi bond. Okay, and there will be OH. Now this oxygen is forming 3 bonds, so this will be 1 positive here. Right? Also, let us draw the next structure here. The negative will be shifted to this, and this pi bond will be shifted to negative, right? And another resonating structure will be double bond. This is negative, this is double bond, OH, and this is positive. Another resonating structure will be this this negative will be shifted here, this pi bond will be shifted here. Another structure will be this will be pi bond, this will be pi bond, this will be negative, this is double bond, OH, and this will be positive. Okay, next is this negative charge will be shifted here and this pi bond will be shifted here. So this will be pi bond, and this will be OH. Perfect. Is it? Have you drawn 5 resonating structures of phenol? Are you able to draw these structures? Are you able to draw these structures? This is plus M effect. Why this is plus M effect? Because we can see this outer group, the group on the benzene ring, it is donating those electrons to the ring. It is donating those electrons to the ring. That is why it is called plus M effect. Okay. That is why it is called plus M effect. Now let us see one more thing. That is this is the ortho position, this is the meta position, this is para position. Can you see in plus M effect at ortho and para position? This is ortho, this is para, this is again ortho. At ortho and para position, we'll find negative charge here. You will find negative charge here. That means in the resonating structure, when there is a group attached to benzene, which is plus M group, which is providing the electrons, there will be minus charge on ortho and para position. Okay? Thank you, bacha. There will be minus negative charge on ortho and para position. So can you see any charge on meta position? Can you see any charge on meta position out of this? I can't see any charge on meta position. So there will be no effect on meta position. There will be no effect on meta position. So now there will be one thing. If there is one group attached to benzene, that group is plus M effect. That group has plus M effect. That means, and we have some electrophile. We have some electrophile attacking on this group, attacking on this compound. Okay. Some electrophile. Electrophile is electron loving. Somebody who is in love with negative charge. So now it will attack either on ortho or on para position. Okay. Because we know in the resonating structure there is negative charge on ortho and para position. So this electrophile will attack on ortho and para position. Now if we have a nucleophile, nucleophile means that is nucleus loving, that loves positive charge, right? That love nucleus is positive, no? So it loves positive charge. So now if it has to attack on this compound, what will happen? It will attack on the meta position. It will attack on the meta position, and that is how you can tell which will be the product. Will it be a ortho para substitution or it will be a meta substitution, depending on the group. Will it be a plus M group or it will be a minus M group? Okay, understood? Perfect. Ma'am, can we say electron releasing group are minus plus M group? Perfect. Yes. The groups who donate electrons or release electrons, they are plus M groups. Okay, they are plus M groups. They release the electrons and they have negative charge on ortho and para position. So the electrophilic substitution reaction will happen on ortho or para position, and that too out of ortho and para. Para will be the major product because of steric hindrance, because in ortho position, at ortho position, there will be steric hindrance. If the group has substituted here, if the electrophile has substituted here, there will be steric hindrance, and that is why para will be the major product. Okay, you will understand in this in coming lectures of hydrocarbons, aldehyde ketones, and alcohol phenols. In all this, you will understand this with more clarity, with more reactions. Okay. Perfect. Perfect. Understood? Perfect. Happy to know that. Now let us do minus M effect. Okay. So this is the minus M group. NO2 is a minus M group. Let us see. I don't know why students find this very difficult. I don't know why students find this very difficult. It is very easy to draw this. I'm just going to give you one trick. Okay, I'm just going to give you one trick. See, after this trick, you will be able to draw structures of minus M also very easily. Okay, let us understand that. So the groups which shows plus M effect are the ones which are directly attached to that ring with a lone pair. Okay, the groups which are directly attached to that ring and have one lone pair, at least one lone pair on it, are called plus M effect. That means if somebody is plus M, that group should have one lone pair over that atom which is directly attached to that ring. Understood? Understood? Yes, ma'am. Adipoli. Perfect. Okay, Adipoli. Understand this? If this is the benzene ring, if this is the benzene ring, if this is the benzene ring, the group directly attached to it must have a lone pair, at least one lone pair on it, so that it is able to donate those lone pair to the give. Only then, to the ring, only then this will be plus M. Only then this group will have plus M effect. Okay? Clear to everyone? Now let us understand what are the conditions for minus M effect. What are the conditions for minus M effect? Let us understand that. So the group, understand this very carefully, listen to this very carefully. So this is the group that is directly attached to this ring. The group that is directly attached to this ring must be, the group that is directly attached to this ring must be attached to an atom that is double bonded to it. Okay? Let it be X. That means the group that is directly attached to this ring must have a double bonded atom next to it. Understood? This group is attached to one another atom with a double bond. This is the condition. And one more condition is that the condition is that this X must have more electronegativity than this group. Okay? This X must be more electronegative than this G group. Understood that? So let us consider these examples. For example, you have COOH. Now, will this be a minus M or this will be a plus M? Tell me, will this be a minus M or this will be a plus M? Will this be a minus M group or this will be a plus M group? Understand? Students, tell me, will this be minus M or this will be plus M? Will this be minus M or this will be plus M? Fastly, everyone in the chat box, tell me, will this be minus M? Perfect. Somebody is saying plus M. Oh, ouch. Listen to this very carefully. I told you, plus M is something if the group directly attached to the ring should have lone pair above it. Okay? If the group that is directly attached to the ring is connected to a bond, is connected to an atom with a double bond, and that atom is more electronegative than this group G, then it will show minus M effect. Now, you see, this ring is directly connected to one atom, that is carbon. And this carbon is directly attached to one atom which is more electronegative than this atom. And they are connected to each other with this double bond. Now, what will happen here? What will happen here? Because this is more electronegative, it will pull out the electrons. Okay, it will pull out the electrons. And then what will happen here? It will pull out the electrons from this. And it will pull out the electrons from this. Okay, this will happen here. Understood this? Understood this? Okay, sorry, we'll correct it. Okay. Now let me give you another example. Let me ask you another example straight. Tell me, will this show this is A, this is B, this is C. Out of these, which will show minus M and which will show plus M? Out of these, which will show minus M and which will show plus M? I don't want you to cram it. Okay, which will show minus M, which will show plus M? Fastly in the chat box, which will show minus M, which will show plus M? Perfect. Yes, very good. Tell me, bacha, which will show minus M, which will show plus M? Fastly. Perfect, perfect, perfect. Adipoli. Yes, very good. So A, this is directly attached to the ring and it is having lone pair. That means it is going to donate those electrons. That means it is showing plus M effect. Okay, this also have lone pair directly attached to the ring. That is why it will show plus M effect. Now, this COR, if we talk about this COOR, this will be C double bond O, this is R, right? Now, this ring will be directly connected to an atom which is further connected to one atom with a double bond, and this oxygen is more electronegative than this carbon. That means this will show minus M effect. It is going to pull those electrons towards itself. Okay? Perfect. Are you able to understand this? Are you able to understand this? Now, talking about this CHO group, in this way you will be able to find any group that is showing plus M or minus M effect. And you will be asked this question in exam in any form. There may be any reaction given. They may directly ask you plus M and minus M. They may ask you this in a complex question. But these things will be asked in the exam. Okay? Now, for this, as you know, this carbon is connected to another atom which is with a double bond, and this oxygen is more electronegative than this atom. That means it will show plus M effect. It will show minus M effect. It is going to pull these electrons. It is going to pull these electrons. Right? Okay? It is going to withdraw these electrons from the ring. If it is withdrawing those electrons from the ring, that means it is showing minus M effect. Okay? Sure. Perfect. Perfect. So now let us see how you will draw the structure of NO2. Now this will be very easy for you. Now I am telling you this will be very easy for you, like a butter. Like a butter, this will be very easy for you. Okay? Perfect. Perfect. Okay. So now let us draw the structures. Now what will happen here? This is N, this is O negative, and this is double bond O. Right? Now, this ring is directly connected to an atom which is further connected to an atom which is more electronegative than nitrogen. Oxygen is more electronegative than nitrogen, and these two are connected with a double bond. That means it will show minus M effect. That means it will show minus M effect. Perfect. I'm talking, I'm so sorry. I was about to say bahut badhiya. Okay, that is like very good. Perfect. Okay, so now this oxygen will pull out the electrons. This oxygen will pull out the electrons from this double bond to itself. Okay, this oxygen is going to pull out the electrons from this double bond to itself, and this nitrogen will pull out the electrons from the ring to itself, right? And the resonating structure will be, I'm drawing the resonating structure here. This is double bond, this is double bond, this is nitrogen, this is single bond O negative, because the pi electron is converted into negative charge now. And this is already negative charge, and this pi electron is converted to pi bond here also. This will be double bond, and this is positive, because nitrogen is forming 4 bonds here. So this is the first resonating structure. Okay. Now, second resonating structure. Okay. So now, as there was a double bond initially, but now this pi bond electrons has moved from this to this place. So there will be one positive charge on this carbon. So now the electrical neutrality is maintained only. Okay. There are 2 negative, 2 positive, and there was 1 positive, 1 negative. This 1 negative and 1 positive means Before also it was neutral and even now it is neutral. Okay. Two negative and two positive cancel each other. Like this is simple maths, yaar. This is simple maths. Okay. So now after this, what will happen? So now what will happen? Now this bond will be shifted here. Now what will happen? This bond will be shifted here, and that will be double bond nitrogen. This is O negative. This is O negative. Are you drawing it with me? If you are not able to draw, then let me know. If you are not able to draw this, let me know. And if you are able to draw, then also let me know. Okay? Because this is a very important resonating structure that most of the students get stuck in. Okay? That is why I am drawing this with you. Right? This is a very basic thing. Right? This is a very basic thing, and you need to draw these structures. Okay? If you are not able to draw these structures, you will stuck somewhere in the higher level questions. Okay? This bond will be shifted here, and now this bond will be shifted here, right? And this will be double bond, double bond, double bond. This is single bond, N, O, and this is O negative. Why this is double bond? This negative charge has shifted here. Okay, this pi bond has shifted here. Okay, that is why again it was earlier like this, now it is like this. There are 5 resonating structures in total, and these two structures are different. Okay, they are equivalent but they are different structures. Okay, perfect. Able to draw, can draw, ma'am. Able to draw, perfect. A positive charge is there. Where, bacha? Where is the positive charge? Okay. Yeah, there is positive charge here. Yes, very good, sir. Very good. If you are able to find the correction here, then you are on the right track. Okay? You are on the right track. Ma'am, there is positive on the nitrogen. Very good. Very good. I am drawing the, we are always stuck in these arrows even after so much practice. Just relax your mind and draw it with more patience. You will be able to draw it. Okay? You will be able to draw it. I also used to get stuck when I was in 11th. I do remember when I was in 11th, I used to find these structures very difficult. But now I find this very easy. But it's all about practice. Okay, it's all about practice. It's sharat. Okay, it's sharat. Okay, so sorry. Yeah. So basically, these structures aren't the real structures. Yes, these are not the real structures. Oh, ma'am, that hit so hard, ma'am. These are not the real structures. Then why are we even drawing these structures? Yes, these are hypothetical structures. There is the resonance hybrid. That will be the real one. That will be a combination of all these structures. Right? Okay? Okay, perfect. Yes. Almost we are going to wrap up this lecture. Okay? We're going to wrap up this. Yes, perfect. Okay, so now let us see the examples of this. The examples of plus m and minus m. Here are the examples of plus m and minus m. Right? These are examples of plus m and minus m. Plus m has lone pair. This also has lone pair. Right? Lone pair. Now somebody will say, trust me, one student has asked me this question. Ma'am, why this is not showing minus M effect? Ma'am, there is carbon and the carbon is having double bond with oxygen. What I told you, the ring must be directly attached to that carbon. Only minus M will be shown when the ring is directly attached to that carbon, which is further attached to a carbon which is with a double bond, which is further attached to an atom with a double bond, which is more electronegative than this atom that is directly attached to this ring. Okay, and that is why here we have oxygen that is directly attached. Oxygen is directly attached, and oxygen is not further attached to any other atom with a double bond. That is why this is showing plus N, not minus N. Understood? Yes, because O is attached to the ring. Very good. Now this will also show plus N because this nitrogen is not. If this carbon is attached to the ring, then it will show minus N. But here, this nitrogen is attached to this ring. And here also you can see The ring is directly attached to this carbon, further to double bond to this oxygen. Oxygen is more electronegative than this carbon. Same with COH, same with this, same with this, same with this, same with this. Okay. Now, ma'am, here there is triple bond. Triple bond. Triple bond means also triple and double bond means 5 bonds only, na? So this will also be included. Okay. This will also be included. Okay. So go through these examples and tell me, is there any example that you are not able to understand? Is there any example that you are not able to understand if this is plus m or minus m? Is there any example out of these? I am so happy that you are religiously watching this live. I am so happy on that. Okay, these kind of students, I love these kind of students. They make me work hard for them more, right? Yes, perfect. Yes, it will help predicting the products. Yes, everything is clear, perfect. Now, one more thing about minus M effect. Minus M effect, one more thing about this. Now, can you see at ortho and para position? This is ortho position, this is meta position, this is para position. Ortho position, meta position, para position. Oh my Prabhu. Prabhu means God. Oh my Prabhu. Okay. Oh my Prabhu means God. Oh my Prabhu. Okay. So O-M-P. O-M-P. Right? So now, as you can see, at ortho and para position, there is positive charge. Okay. There is positive charge on ortho and para position. Ortho and para position, we have positive charge. This means that at para position, there is no effect. There is no effect. So, if we have a minus M group attached to it, if some electrophile is attacking on this compound, then it will get substituted on meta position. On meta position, because comparatively meta will be more meta will have more electron density as compared to ortho and para position, because in the resonating structure ortho and para position are electron deficient. Understood this? Understood this? Oh my pa, yeah, oh my Prabhu, whatever you like. Okay? Yes. Perfect. It will be meta-directing. For electrophile, it will be meta-directing. Okay? Perfect. Understood this? Have you understood this? Understood this? One more thing I want to tell you, because you are religiously watching this. So one more clarity on this topic. One more clarity on this topic. Guys, see, this topic is also very, very important. This also I want to cover it today only. Okay. So, you know what? If we say there is plus M group, it means it is giving the electrons to that ring. Okay. It is giving the electrons to that ring. It means it is activating that ring. It is activating that ring. Activating the ring. Okay. So, plus M groups are usually activating groups. Okay. Plus M groups are usually activating groups. Yes, they will be asked directly or indirectly. They will be asked. Okay. They will be asked directly or indirectly. These kind of questions will be asked. Some concept related to these topics will be asked. I'm telling you that. Okay. Because these concepts are very important. Very, very important. So now, all the usually plus M groups are activating groups. Okay. And also we know plus M groups are ortho. Here I am talking about an electrophile. Okay. Here I am talking about with respect to electrophile. With respect to electrophile I am talking about, because it will provide the electrons, so the ring will be activating. And moreover, plus M effect, the ortho and para position has negative charge. So they are orthopara directing. They are orthopara directing, right? This is with respect to electrophile. With respect to electrophile. With respect to electrophilic substitution reaction, plus M group is always activating, right? Activating groups होते हैं. They're activating groups, and they're also ortho and para directing. That means ortho and para have negative charge, so any electrophile coming will attack on ortho and para position. Okay, clear to everyone? Now also, if you have minus M group, this minus M group will be deactivating. That means it will take out the electrons from that ring. Okay, it will take out the electrons from that ring. That means it is deactivating group. Okay, that means it is deactivating group. Now next thing is, if it is deactivating group, then what it will do? If it is a deactivating group, then bacha, it will be meta directing. It will be meta directing, because we know at meta position, when the group is minus I effect, the electrophilic attack, the electrophilic substitution will occur on meta position. The groups will be meta directing, right? Clear on this part? Plus M groups are activating group and they are ortho and para directing for electrophilic substitution. Minus M groups are deactivating group. They pull the electrons towards itself. They are meta directing. Electrophilic substitution reaction will occur on the meta position. Clear to everyone? Now there is one exception to that. Tell me one thing about halogens. These are exceptional. Okay, this is one exception. Let us see what is the exception. Okay, so halogens like chlorine have lone pairs on it. So what we think, it will be showing plus M effect. Right? And usually mesomeric effect is stronger than inductive effect. That is why for other groups I have not considered the inductive effect. Okay, for other groups I have not considered the inductive effect, right? Why so? Because mesomeric effect is dominating than inductive effect. For example, if I take the example of OH, it is plus M, but it is minus I, right? It shows plus M effect, but it also shows minus I effect. So is this activating? Is this deactivating? What to do, ma'am? The reason is mesomeric effects are always dominating than inductive effect. That is why in all other cases, we don't even think about inductive effect. We just say this is electron donating. It donates the electron. Okay. We consider plus M effect. That's why we say it is activating the ring. It is activating the rings. Okay? Understood? Understood this point? If I talk about any of these groups here, this is also showing plus M and minus I. This is also showing plus M and minus I. Also plus M and minus. This is a very good minus I effect. NH2 has a very good minus I effect. Okay, and also this is also showing plus M and minus I effect. But mesomeric effect is dominating over inductive effect. That is why all these groups are activating the ring. Okay, all these groups are activating the ring. But when it comes to halogens, halogens also show plus M and minus I effect. They also show plus M and minus I effect, right? But now these also show plus M and minus I effect. But here mesomeric effect is not dominating, but inductive effect is dominating. Understand this? This is the exception here. That in case of halogens, plus M effect is not dominating, but rather minus I effect is dominating. Inductive effect is dominating over mesomeric effect. and that is why, that is the reason this is deactivating group. This is deactivating group. First thing is it is deactivating group. Second thing is because it is showing plus M effect. Because if we see the resonating structures, if we see the resonating structure of Ca halogen, what will happen? There will be ortho and para position. There will be negative charge only. You will see here will be negative charge. The resonance will be same as in case of phenol. So that is why there will be negative charge on the ortho and para position, and that is the reason. It will be ortho and para directing. Electrophilic attack will be on ortho and para position. Understood? In case of halogens, the exception is they are deactivating, but they are ortho and para directing. Else, all other groups are activating and ortho para directing. Either they are activating and ortho and para directing, or they are deactivating and meta directing. But in case of halogens, because inductive effect is dominating, because inductive effect is dominating over mesomeric effect, that is the reason this is deactivating group. It is pulling the electron with more strength, but when it comes to electrophilic substitution, this is the ortho para directing group. Okay. So if we say if you are asked this question, you have been asked this question in previous year also. You have this OH, you have this chlorine, you have this chlorine or any halogen here. Rate of reaction for electrophilic substitution will be more for phenol than this. Why? Have you understood this thing? This is phenol and this is let it be, this is chlorine. This is, let it be any halogen like chlorine. This is chlorobenzene, right? Chlorobenzene, halobenzene, anything. So I have written chlorobenzene. Now, this is a deactivating group. The electrophilic substitution will occur on ortho and para position only. The product will be ortho and para substituted only. But the rate of reaction will be more with phenol than with chlorobenzene. What is the reason behind that? The reason is this is more activating. This has activated the ring. This has deactivated the ring. Activated means it has more electron density. Electron density is more. As OH is activating. Okay. Chlorine is deactivating. It is pulling the electron from the ring. That is why electron density here is less. Electron density is less. And that is why, I can write it here. Cl is deactivating. That is why this is deactivating. The rate of reaction on phenol will be more for electrophilic substitution reaction. Okay? Any student who have not understood this point, any students with very important point, and this has been asked in PYQs. Okay? You can see this in PYQs. This is asked. You can just open your syllabus for NEET. They have clearly mentioned this topic. Directive influence of plus M and minus M. This is the directive influence. Okay, this is the ortho para directing, or they are meta directing. This is the directive influence, and this is the rate of reaction. These two will form ortho and para substituted product. Ortho and para substituted. Here also this is ortho and para substituted. Okay, understood this? Because of inductive effect is more dominating in halogens. That is why it is a deactivating group, and that is why rate of reaction for electrophilic substitution will be less here, because the electron density is less here as compared to other groups that are plus M. Okay, understood these? These exceptions are amazing. Yeah, they are amazing, and they ask questions from these exceptions only, right? Okay, perfect. So any doubt in today's lecture? Any doubt in today's lecture, bacha? Any doubt in today's lecture? Do let me know if you see any doubt in today's lecture. So this is the question for your homework. This is the question for your homework. You need to tell me which out of these which is more stable. Okay, just the stability order. The stability order of, okay, this is A, this is B, this is C, this is D. This is your homework. Just take a screenshot of this and write down in the comment section. In the next class, I am surely going to answer the homework for last 3 sessions. Okay? Okay? Perfect. Thank you, bacha. Thank you so much. Thank you so much. I hope so you have understood everything. If there is any doubt, if you will revisit this lecture and you found, okay, I have not understood this, ma'am, just write down in the comment section that, ma'am, please, I have not understood this point. Please clear this in the next session. Okay? Okay? Perfect. Perfect. So it's almost 11 and we are here studying. So what can be, this is the amount of dedication that I need from NEET students. If you have this much dedication for study, then you will surely crack NEET, right? So many students are here, they are stable, they are not going from here or there. That is why they are the reason that we are constantly teaching you on this platform, and they are the reason that we get so motivated by seeing your motivation. Actually, you are the ones who motivate us, right? Yes. Yes, perfect. I'm so happy that you are enjoying these sessions. And in the next session, we have completed what we have completed. We have completed inductive effect, IUPAC naming resonance. In the next session, I am going to teach you inductive. I am going to teach you hyperconjugation and aromaticity. Okay, hyperconjugation and aromaticity. We will cover this in the next session. Okay, perfect. Now, first understood. Thank you so much. Thank you so much, bacha. Thank you so much. Do practice the questions. Do practice the PYQs. Do practice the NCERT questions. And also read the NCERT. Okay? Do not crack the NCERT. Just read. If you can understand the points given, if you can see the points highlighted in the NCERT. And also solve the NCERT in-text question, NCERT exercise and PYQs based on these resonance. Okay? Perfect. Yes. She's saying physics still left for revision. Yes, you have your time now. And I'm going to have my dinner. You also have your dinner. And good night. Have a sound sleep. This is my pet. This is my favorite dialogue, that have a sound sleep. Right? My old students already know this. Now you also know this. Have a sound sleep. Whenever there is a session at this hour, I usually say have a sound sleep. Not a ghosty sleep. Okay? Just take good dreams about you clearing NEET and becoming a doctor, and then meeting me and saying, yes, ma'am, we did it. Right? Okay, perfect. Manifest whatever you want to achieve. Manifestation do work. I have manifested this thing, right? And I'm here now. You manifest that thing and you will be there. Okay? Perfect. Okay then, thank you so much. Thank you so much. The lecture is Adipoli. You will write in the chat section. The lecture was Adipoli, ma'am. Okay, perfect. See you soon. Do finish your homework and write it down in the comment section. Bye bye. Take care. Good night.